Thank you, Anastasia. Welcome, everyone. Today, we're going to be talking about how data science is more than just statistics, and I'm going to be exposing lots of Wolfram's tools that you can use to um, do more sophisticated data science. Okay, so it's a very large tool set. We're going to try and explore a lot of it today. So I'm scheduled to talk for about an hour and a half. This has been streamed on YouTube and is also on Big Marker. So any questions you have, you can use the Q&A panel in Big Marker or the live chat on YouTube. Okay. So traditionally, I would say that data science has just been treated as doing lots and lots of statistics on your data. Okay. Companies are really interested at the moment in big data, but perhaps they prioritize the, the generation or the um, obtaining of large amounts of data, but are actually only doing the same calculations over and over again. So this is an example of essentially just doing simple statistics when you could open yourself up to the entire range of possibilities that computation brings. So the, the the aim here is to kind of redefine data science as computation with data. And what does computation actually mean? Well, it can take on many different meanings. So here are just a few of those, and it includes modeling and visualization with graphics, machine learning, signal processing, um, even things like uh, viewing and survival analyses, that kind of thing. And what what you'll often hear me talking about here is that even if you're not an expert in a particular area, if you understand the tool set, you can still execute expert-like operations. Okay? And you don't necessarily have to stay in your lane, so to speak. If you're a data scientist, you can employ machine learning techniques. Okay? And yes, Wolfram language enables you to do this, and we'll go through lots of examples today, explaining how. Okay. So we'll start with kind of basic examples, but really quite neat. These were taken from, I guess, personal personal pet projects that someone here at Wolfram was undertaking, and it is really starting with the basics. So we are doing some counting here in the traditional sense, but we end up with some nice visualizations, and I believe it still classes as doing data science, even though it doesn't look like traditional data science. But I think it is still under this abstract umbrella that is counting. So let's take an example like text, okay? The text of a book. What does counting mean in that sense? So the book of interest here is Lord of the Flies. If anyone has read it, these are three of the main characters. We have Jack, I believe a kind of antagonist, the Beast, and Ralph, um, from whose perspective we read the book, I believe. Anyway, so looking at the word frequency of these three characters as the text goes on might give you some idea of how the plot unfolds. Okay, so there's an initial spike here when they find the beast, and then it goes way up when the entire book becomes all about this beast. Um, and that also coincides with Jack, the kind of antagonist, resuming some level of attaining some level of power within the group. And yeah, so this gives us some idea of what's happening in the book just from counting words and then displaying it in this nice plot. And you can see the code for this if you like. We can just, you can see we've imported the text file containing the entire book. And we've looked at string position of the name. And then we have a many overlaid plots. So very simple. The bulk of the work here is being done by this string position as a function of a name, and then this name can be Jack, the Beast, or Ralph. Great. Okay, so that's counting. Um, and yes, it gives us some idea of the plot, but maybe instead of just counting the word, you could try and get something like the meaning of the words. So that's where classification comes in. And I'll start with a basic example where we're going to classify the sentiment of the text sentences within the Lord of the Flies book. And then we're going to take the one that is maximal in positive sentiment. Okay, so this is going to do some work here. It's using a built-in classifier that you have access to in the Wolfram language, which is a sentiment classifier. And then maximal by just takes the one that has the highest positive sentiment. Okay, so we have our answer. So this is the sentence that was deemed to have the highest probability of being a positive sentiment, which makes sense. It's a reasonably positive sentence. It turns out they don't really have fun on the island, but well, okay. Now that just gave us one sentence, but what if we want a similar picture of the kind of plot uh, based in this sentiment analysis? So what we'll do here is we'll overlay on the word frequency plot above. We will overlay some measure of the sentiment as the book goes on. So what happens here is any given sentence is classified according to its sentiment. If the highest probability sentiment is positive, we give it a score of 1. Negative, we give it a score of -1. Neutral, it gets 0. So as you'll see in a second, um, if you have many consecutive positive sentiment sentences, then the score starts to stack up, and then maybe you have one drops down. It just kind of goes up and down a bit like the stock market or something like this. So this will take a second to compute. And here we are. So this blue line is showing the sentiment over time. So it starts pretty negative, and then they are optimistic about what they'll do on this island with no adults around. Uh, Sentiment kind of drops again, goes up once more when Ralph makes his last ditch attempt, and then it according to this it all ends terribly. Okay. Um, so there, that was a nice look at how we can use computation on text. Images, here's another example. I believe this example was curated because a scientist wanted to make some measurements on these nanoparticles being kind of injected into skin. I think this is. So this is a kind of membrane um, where the particles are injected in, and you need to determine how deep um, these nanoparticles go. So what was being done? I believe there were some rulers being held up to screens. So something very very prone to human error, not very computationally sophisticated at all. So this example was born. And this first piece of code here just takes two of these nanoparticles and then performs some image processing. Okay, so I'll show you the final result. We have the original here. We have a cleaned image where it is just binarized. So every pixel is set to either white or black, 0 or 1. and then a distance transform is calculated. So this gives you some idea of what the pixel value is relative to the background. And then from this, it's actually quite straightforward to use max detect, and then you get the central maxima of each nanoparticle as a single point. And that's what we have here. So it's really just a matter of doing this, scaling it for all of these nanoparticles, and then we can have an image like this, where the centers have been indicated by white crosses. Okay, so this is great. We have some sense that we have abstracted the picture to some coordinate points. But what's really nice is you can then do some more computation on this, and you can make a 3D histogram, which takes into account, the width along this photo and the depth into the skin, perhaps, and then we get a sense of how clustered the points are. And this looks like a kind of bimodal distribution, suggesting that there's underdense area here. I think I can tell, and then um, we have some like higher concentrations here and here. Okay, so yeah, two examples there: text and images, both really just counting, but in a sophisticated way that's making good use of Wolfram's tools. Now we're going to talk about injecting some context. If you've managed to download the notebook, you might see some additional files. In that, there is a shipwrecks.mx file. So this gives you I believe, a list of associations. Just see, just take the first element. Yeah. So you get a list of associations where you have a ship that has been sunk, and you find the date it was sunk, and we have a brief description of this and the coordinates it is believed to have sunk. Okay, so this data structure is quite common in Wolfram language. It's called an association. Oh, association, and it's indicated by these kind of symbols here. It's a bit like a dictionary in Python, if anyone is familiar with Python. Key value pairs is the main thing. Okay, so that was a brief aside. What we're going to do is show off the tabular functionality by just wrapping this import of a list of associations around, wrapping tabular around it. And tabular is this brand new function in version 14.2 of Wolfram language, which is a hyper optimized way of handling rectangular data. Okay, it's making use of the type homogeneity within a column. So, for example, it knows that everything in this column with the ship is a string. Every column, every element in the sunk date column is a date, and so on and so on. So this allows you to get real speed advantages in your computation and to deal with very large data. So that's tabular. I encourage you to take a look at this and the many other functions that have come along with it. What we can also do is convert a tabular object to a data set. So this is just another way of kind of showing your data. Data set is very useful when you have nested data, but I just want to show both being used here. And we will go on to use this data set for the rest of our computations, just because um, there are a couple of functions that are set up to use dataset quite nicely. And there is not that much data here, so the speed advantages tabular would give us are not too pronounced. But trust me when I say that the tabular is doing some fantastic things. So if you work with big data yourself and you can use Wolfram language, then you should check out Tabular. Okay, so the first port of call here is to make a word cloud out of the description column. So this taking every description, um, joining it together, and then we're seeing the words that appear most commonly. So U-boat, sunk, HMS, that must be a common name for the ship. And then you can see some kind of geopolitical players that were involved uh, in these sinkings. Okay. In a similar way, we can make a date histogram just using the sunk date column now, showing the very large concentration um, in around the time of World War II. And notice here, we're just taking our data set, giving it a function, and then giving it the column name. Another function we can give it is geolistplot. So we have our coordinates of each ship sinking, and this essentially puts a point on here, assuming that coordinate isn't missing. So we have known coordinates. Um, every ship sinking has a red point on this plot. We can change the function to a geosmooth histogram if we like. So this if you're not interested in every point, you just want a kind of broad idea of where the majority of ships sunk, then this is a good idea. And you are free to choose the kind of level of smoothing, the kind of distribution um, that the smooth histogram actually chooses here. Okay, so I don't want to get sidetracked here because this whole thing was about injecting context, and so far we've just kind of made some plots of the different columns. But what if we could call upon some other data that's available to us using Wolfram language, and and then see if these shipwrecks, um, if we can draw some more interesting insights from these shipwrecks. Okay, so the way we will do that is by defining a longitude latitude box. Okay, so it's as simple as just giving it a minimum and maximum longitude and latitude, and then here I just define a table of geopositions. I'll show you what that looks like here. Maybe just the first 10. Okay, so we're essentially sampling the globe at these geopositions. And what we do here is get the sea data. So we can use this built-in function geo-elevation data to get the geo-elevation at each value inside box array. So that's each latitude longitude pair. We're essentially getting how deep is the sea. Okay, so elevation is doesn't mean necessarily that the thing is above ground. These values may well be negative. Okay, and then there's a bit of a more complicated workflow here. So if you're familiar with Wolfram language, then you can take a closer look at this. But what's I'll just give you the broad look at this, and that is that we check if the coordinates of the shipwreck lies inside the box that we defined here. Okay, and if it does, we want to assign a point that we can keep and then store in a kind of 3D graphic. What that's doing is essentially like taking the coordinates and the depth at those coordinates, and then saying, okay, if the ship has actually wrecked, it has likely sunk to the bottom of the sea, and then maybe we have some idea of where it actually is now. Okay, so that's what we're doing here, making sure to include shipwrecks that don't have any missing coordinates. And I also put a link here to this to the function that is called transform missing, which is one of the functions that came with tabular. So instead of just ignoring missing values, you can actually give it a function to say, what do you want to replace these missing values with? Okay, do you want to replace them with 0, or maybe the mean of your data set, or the median, things like that. Anyway, so we have some depth data now, so we can plot a histogram of the depth data, and then finally we can make a 3D plot where we overlay the sunk ships on the geo elevation data in that latitude longitude box that we defined earlier. Okay, and this is a very nice interactive 3D graphic that you can get. I would say exclusively in Wolfram language with so little code. Great. So now maybe we have some context for why these ships sank where they did. Maybe there's some undersea feature that caused the shipwreck. What's important is now our data is in a nice computable form such that we can test these hypotheses and very um, seamlessly make these visualizations. Um, Another example, a bit more perhaps appropriate for your day-to-day life, is picking somewhere to go out to eat. So this data is taken from the food hygiene rating scale from 1 to 5 we have in the UK, for the city of Oxford. Okay, so we just have a rectangular data set with the business name, postcode, and the rating that they got on their last kind of hygiene audit. Um, so you might want to say, okay, as a city, where are the areas where the food hygiene is better, and, and where is it worse? So again, we're back to kind of geographic plots, and this is what we have. So as you can see, we do have a majority of fives, but there are some ones here and there which you'd probably want to avoid. So this gives you individual point for each one, but as I said before, perhaps you just want to see the trend, and then this is where the darker areas in blue here are the lower ranked zones. And then we can also compare this on a national scale too. So what seems to be the case is that the cities with the higher populations have a higher probability of not being above like a 4.5 out of 5. Because as you can see here, that relatively on, um, from 0 to 5, the scores are on average closer to 5. However, you still see some emerging trends like this. Okay, so that's a nice example, just scraping a kind of public API and then getting all of this data, and everyone intuitively knows what it means. Okay, everyone's seen these hygiene scales before. Uh, I just For those of you who don't know what I'm talking about, I will just show what I mean. This is what I mean. Okay, so if you've been in a restaurant and they serve food anywhere, you should see something like this. Okay? And this is a very similar thing where uh, we can get the number and severity and et cetera, for accidents that happen in a given location. And then, as you can see here, this is where dataset comes in, because this data is not as simple as just rows and columns, because as you might expect with a vehicle accident, you can have more than one vehicle involved. So this row whilst it is just one accident, has taken into account two different vehicles, one being a light goods vehicle and one being a bicycle. You got the age information of the casualty, how severe it was, and essentially which one they were. So in this case, the casualty was a 21-year-old, um, and they were the driver of the pedal cycle. So this one. Okay, so we can kind of pick apart this data set all we want, but what we're really interested in is the geographic trend again. Okay. This next example is taken from a consulting project that was done here at Wolfram Research, where the client was the creators of a supersonic car, and they had all of this data on various parts of the system, uh, real-time information on when the driver of the car pressed the accelerator, um, or the brake, or even deployed a parachute. I think that was attached to the back. So I believe this was a quite a successful project, and I have some plots here which kind of show the key findings from this project, um, with an emphasis on changing the viewpoint. Okay, so traditionally, you have some data, maybe you just plot it against time, and then you try and um, figure out what something's doing with time. Because humans, we can make sense of, like, we experience the passage of time every day. So uh, you can kind of intuitively imagine something changing with time. But when you're dealing with high dimensional data, there are really many things you can plot against many other things. Um, so a plot against time isn't always that useful. Or maybe you can plot one thing against time, but by applying some calculus, you can get a whole other thing that's actually more useful. So that's what this second plot is. But first, here is the raw data. So we have the RPM of the wheels and the suspension load. Okay, so here we have the application of some calculus on the velocity profile, such that you get acceleration, and then overlaid onto the acceleration, you have the whether the driver pressed the throttle. Okay, so you can see it's kind of creeping up here, causing maximum acceleration, and then it looks like the driver took his or her foot off the throttle, and then the acceleration went from very, very positive to very negative. Okay, so it's then decelerating. Uh, yeah, perhaps you've got air resistance building up in this time as well. Okay, yeah. So on the topic of kind of expanding the tool set, um, one of the things that the consultants working on this did is look at, let's say, the load on one of the wheels, and then they executed what's called a continuous wavelet transform. And you can look at the documentation of this here. Just pull up the documentation page. Uh, this gives you some idea of the frequencies and vibrations that are at play in a set of signals. Okay, so what this looks like is we have a lots of um, lots of signals of a particular type here, and then a really steep spike in signals of another type. Okay, so this y-axis is showing you, I think, like high frequency vibrations versus low frequency vibrations. And I believe what the engineer of this supersonic car was able to determine from this plot is that around this time, one of the wheels went supersonic. Okay, so just by applying some uh, some more sophisticated computation in the form of a continuous wavelet transform, we're able to kind of tease out these signals from the noise. Okay, I quite like this example because um, it's 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 something that's quite intuitive, but is often not explored in a very kind of creative and computational way. So we've got a portfolio, um, an example portfolio here where we have stock ticker symbols. As you can see, we have the same stocks in the rows and the columns. So on the leading diagonal, we have entirely ones because this stock is perfectly 100% correlated with itself. Okay, and then we have a bunch of other numbers. So let's visualize this. So this is the entirety of the correlation matrix. And then we can actually use this kind of filter to filter out anything that is below some threshold. Hmm. For some reason it's not responding very well to this dynamic, but okay. You'll have to forgive the kind of red lines here. I'm not really sure why that's happening, but yeah, as you can see, as I slide this, it essentially removes anything that doesn't have higher than a zero point 0.3 correlation. And you can increase this to 0.55 and we have even fewer. Okay, another nice way to show this is the graph communities that arise when you remove um, or when you have this correlation filter. So if we have a very high correlation threshold, we really just have these two communities where, however, if you lower this threshold, you're kind of being a bit more forgiving as to what you say is part of a certain community. Okay, it seems that it started to behave now. I'm not sure what happened there. Um, yeah, so this is an example of a community graph plot, um, and it's a really nice interactive way of exploring something typically kind of boring, which is like financial portfolio correlations, all in this one interactive tab view interface that is just powered by Wolfram language code. So this will have Wolfram language code behind. This example is talking about how you might handle completely different data. Okay, this data is not rectangular. Um, it's not nested at all. It is an audio file. Okay, so if you have the notebook, you can play this audio, and it's kind of I believe it's a speeding car passing a pedestrian. So this is the raw audio file, which you can handle in the Wolfram language. You can store an audio file just as you would any other data. And then this is an example, just showing which neural network we use to kind of handle audio files of this nature. And it's called CREP here, which stands for Convolutional Representation for Pitch Estimation. And this, I believe, is a plot of that pitch as a function of time. As you can see here, this audio file is only 5 seconds long, and this plot is showing the pitch as a function of time. So those of you who are familiar with physics might think that as a car races past, you have this Doppler shift in frequency. So we can actually fit a Doppler shift model to the data. Okay, so we need the speed of sound, um, we need the time, obviously, and then we have all these free parameters like the initial frequency. You can even get some measure of how far away the object is, which is nice. Yeah, and then these are all the free parameters that come out at the end. So we have the source frequency, the time at the nearest point, the distance at the well, I guess this is distance at closest approach, and what's important is the speed that the car was actually going. So I think this is in um, meters per second. Would that make sense? Let me check. Do a quick unit convert here. Yeah, meters per second. So this looks like it was meters per second, which translates to around 45 miles per hour. So I don't know, maybe this was a speeding car in a 40-mile-an-hour zone. And you can see the workflow for this below if you'd like. Okay, I'll just close this a second while I introduce this topic because this is a really important one. Um, when I when I started this talk, I mentioned um, the importance of expanding the tool set that you use. Okay, therefore, if you're a data scientist and you say, "Hey, I don't know anything about machine learning," um, then you're probably not likely to try any machine learning. Okay. Um, However, if you know what you want to do, and it just so happens that you don't know the sophisticated algorithms that are required for machine learning, maybe you just want to declare what you want to do and then let automation take over. So that's what Wolfram language is has has done with these super functions classify and predict. Okay, so these functions are really powerful because yes, you can specify that you want to use, I don't know, a nearest neighbors method or a linear regression method or a random forest method, but you don't actually need to specify this. You can just say, I want to classify my data or I want to predict this column using these columns. And then you have an automated process where it picks out the best method for you. So this, I'm going to show that in action here. So we're going to fetch some example training data from the Wolfram data repository. Uh, this is what it looks like. Again, it's in this tabular format, or I can even show the tabular structure of this data, which gives us some idea of how much of it is missing, etc. and the types. So for each column key, we have a summary here where we have the type, the non-missing count, the missing count, and the byte count. So this is helpful. Um, and yeah, now all we have to do is take our tabular object and say we want to classify it according to whether survived was true or false. So whether these people on the Titanic, for whom we have their class, age, and sex, whether they died or survived. Okay, that's the objective here. So we use T data goes to survived. Here I've just put a time goal on. You don't really need a time goal here, but if I didn't put this on, it would essentially be done too quickly, and we wouldn't be able to see all the interesting things that are happening behind the scenes. So let's have a look. So this is our learning curve. We have a current best method, but if I click the arrow here, we can see the learning curves for all of these algorithms. Okay, so they're kind of in a race to the one with the lowest loss. And as you can see, eventually it switched to gradient boosted trees. So that's the method that we'll end up with. And we have a classifier function here. So now we can come up with some fictitious passenger, feed them into this classifier, and then get some probabilistic estimate as to whether they died or survived. So I'm a 24-year-old male. Let's see how I would do in each of the classes. Nope. Well, if I didn't survive in first class, it's not looking very good for second or third. So, and you can also query it with the probabilities too. Oh, seems I do this on the next line. Okay. So it's close, but in the end, the classifier picks the highest probability class, which in this case is false. Wow. So as you can see, the probability of surviving goes from 40% for a first class 24-year-old male to 10%. And then we can do something a bit more sophisticated here. We can plot the survival probability. Oh, no, perhaps this is the dying probability of a first class male as their age varies from 0 to 60. Yeah. So what this is showing is that the young people, children were prioritized, and it was not looking as good as you got older as a male in first class, but these people had the courage to sacrifice themselves, I suppose. Great. So that was a whistle stop tour of the classify function. I hope you found that interesting. We can also use it on images. So we have lots of photos here of an image, and then whether it was taken in the day or taken in the night. So it's kind of classic supervised machine learning here. I'm just going to define, well, run the classifier. So here we didn't even define the data outside of classify. We just put the data straight into the classify function. Okay, so it knows the input type is an image, and we have two classes, day and night. And then we can run this classifier on some new images here. Then we can see how well it does. So it looks like it got this one, this one, this one, this one all correct, but it got this one incorrect because we have a black hood of a car, which it has confused with the dark of the night sky. Okay. So that was supervised machine learning, very useful in data science, but sometimes you may have to carry out some unsupervised learning. And I'm going to show that here with a data set of pictures of dogs. So here's our data set. And we're going to use this function feature space plot, which essentially creates some notion of similarity between these data points. Um, and then plots them close to one another if they are deemed similar in this way. And it's not always easy to understand what this similarity means because it's the computer um, kind of deciding what makes any two given pictures of a dog similar. And that might be different to a kind of human's interpretation of what makes two dogs similar, or what makes a dog in the first place. Okay, so let's run this. Have to do some pre-processing, and then we have these kind of broadly, we have three groups of pictures here where it seems to have done a good job of putting the same breed of dog next to others. Okay. Um, you can look in the documentation for feature space plot as well, and there's some quite interesting examples of even like countries' flags, for example, and you can start to see flags with similar colors kind of clustering. So that examples like that, it's a bit more obvious what's going on. Um, okay, and now we want a feature nearest, where this creates a nearest function, so we can actually apply this function to new data, test data. Okay, so here's our nearest function, and then we can run it uh, on a new data set called test dogs. So this is what this looks like. um, this one might be hard because, well, personally, I just saw the human in this photo. I didn't even realize they were carrying a dog until I looked closer. And then things like this, for example, it might it it might miss the forest for the trees, so to speak, and try to classify this green grass as one of these species of dogs. So you've kind of got to take your human bias out of the equation here and think about um, what features would a computer pick out on these images. Okay, so let's see. So what this does is it takes one of these images and then finds the nearest dog photo in this data set to it. So it looks like it's actually done quite a good job here. Hmm. This example, it's all about sensitivity analysis, really. I think I'm going to skip it for now because there are some additional things I want to show at the end, including the notebook assistant. But yeah, just as we saw classify before, this is a good example for predict, where we are predicting the wine quality from some data set, uh, given lots of properties of the wine. Okay, and then yeah, you can obtain things like the Sharp values, which show the impact of any given feature on ultimately the thing you're trying to predict. And there's very nice ways of kind of illustrating these Sharp values visually. Okay. So the message here is automation after computation. Uh, and I suppose what it's getting at is um, if you learn the tools very well that you have access to in in Wolfram language, for example, the deploying of your app or classifier, if you want to share that with others, you don't necessarily have to kind of offload it onto some specialist app, like like some developer who um, is a specialist in app deployment, for example, because the process of deploying it has been simplified such that you can actually deploy straight to the cloud from the notebook. So what this is, the example used here is a city bikes example, where this is essentially an online database that has support for more than 400 cities, and it finds out where bike sharing services are. So if anyone here has been to, um, I don't know, a different city, and you see the bike sharing service that they have, of course, it's not all the same. It's very different in different cities, but this this database called City Bikes has tried to integrate all of this together, and they have a um, API that we can access, and that's exactly what we do here. So we use a dynamic module. We set our URL, and I believe this has a default city of London, but then we also incorporate a action menu where you can choose a city yourself, and then we just have to kind of use the API, um, import the data for that city, and show it on a geographic plot. So we have this menu here, so we can click this, and it opens a very many cities here. And then I want to kind of pick one that I think will actually have some bikes available. Um, let's try. Let's try Dresden. So we're just going to download some geotiles to actually make this plot. Okay, so all the bikes are here. For some reason, I'm not sure if this is a bug on our end or on the city bikes end, but it seems to include a bike that's in a completely different city to Dresden, um, in this plot. I'm fascinated to see what's going on there. But let's actually choose a different city. Um, Basel. Okay. Is reasonable. But I think when they're all the same color, it actually means that these are the stops, but there's actually no bikes at them. So it's perhaps not the most useful. Uh, Try Austin, Texas. Okay, nice. All right. So yeah, you've seen me play around with there. You can have a play with this yourself if you have access to the notebook. But if you don't, um, there is the option here to deploy this um, app to the cloud using this cloud deploy thing. So I can also set the permissions to public, and then set the cloud object URL type to an environment such that we can still interact with it there. So we can still use the menu, pick a city, that kind of thing. And we do have other webinars that are a bit more like focused on deploying things to the cloud and creating dashboards and visualizations and that kind of thing. Okay, so I was just logging in on the cloud on another screen, but it should be ready in a second. Okay, sorry for the delay, but here is the availability of bicycles in New York City. So it did take a while to render. That's just because we're on the cloud and not in the desktop, so the performance is a bit slower, but I'm really glad it worked. We have the bike app that we made deployed to the cloud. And really, all you need is the URL, and you can access this yourself. Um, Great. Uh, I encourage you to make your own. In a similar way, we can deploy API functions. Okay, so just before we made this Titanic survival classifier, uh, and here I'm going to deploy it as an API function with some default values. So I'm going to default this to a first class 24-year-old male, and this is our API function. So we have this kind of template. This isn't really useful yet, but we have to deploy it to the cloud in order to actually use it. So I have a new URL. I'm just going to click this URL, and I get false. Okay, that's what returns because the classifier would determine that a first class 24-year-old male would not survive. So this is the default uh, result for the API. I could have also, instead of clicking the URL, I can just use URL execute, which would give me false. However, what if you want to know, okay, I don't just want the default result, I want to give this classifier inputs of my own. I can use this kind of HTTP request language by saying I want the class to be first, age to be 24, but this time I want the sex to be female for this fictitious person, and then again use URL execute, and we get true. So this is great. This is working in real time, and it's showing a lot of automation after the computation. Okay, we've done all the hard work. We've made the classifier. Now we just want to deploy it, and we want that process to be as simple as possible. Okay, so I'd like to summarize here, and then I will bring in the notebook assistant, and we can start to explore some of the things you can do with that. But what I hope I've shown today is that the tool set you have at your fingertips is huge. And the I suppose the reason this has hardly been used traditionally is because it's quite hard to know how to use it well. Now that's where automation comes in, and automation, the whole entire goal of this is to make more aspects of the tool set accessible, and that leaves the human taking on its more human role of asking deeper questions of the data. Okay, because your automated tools are not necessarily going to do everything for you. um, you have to kind of assume the role as of the human in the process. Okay, what I wanted to do next is just show the notebook assistant, which is another new feature in version 14.2, where you can have AI assistants. So this is how the notebook assistant appears in the notebook environment. I'm just going to configure it here and make sure everything's working as it should. And this is generally where I would include the audience and just ask you guys if there's anything you want to see the notebook assistant do in particular. Uh, so I'm just going to bring my brand new notebook over here, and I have a fresh chat with the notebook assistant. So I have some ideas of what I'd like to ask it, kind of similar to what I've been showing today. And because this um, large language model has been, you know, trained on the entirety of the Wolfram ecosystem. It knows about the Wolfram data repository. It knows about the function repository. Okay, so I can ask it questions about this. So I could say, how do I access the fatal collisions dataset from the Wolfram data repository? Uh, okay, so this is an example of some sample tabular data where it's given me some code as to how I would access this. So I can just press insert and evaluate, and it inserts into my notebook and evaluates it. Um, so it hasn't given us a summary, but it's given us some other information. So this is really nice. So it set this data equal to some symbol called data, and then I didn't ask for this, but it's also told me how I might get the dimensions of the data set. Okay, so it's 51 rows, 8 columns. I can also get the column keys and get a description of the columns as well. So this is really nice. And I believe someone asked about, you know, where do they start if they're a beginner? This is a great place to start. So yeah, this column is just the state. So this is a US data set where we have a row for each state. Uh, we have the number of drivers involved in fatal collisions per billion miles, and then how many of these drivers were speeding, how many were alcohol impaired, etc., etc. Okay, so now we can start to ask some deeper questions and see how the notebook assistant does. So I'm going to mm, just make a little command here and say split this into training and testing data and create a predictor model of total fatalities. Okay, so let's see what it came out with. Hmm. Okay, I'm just kind of doing a mini code review in my head here of how it's done, and it looks okay. It's used a random sample of the data and split it into um, well, it's used 70% of the data for training and 30% for testing, which is fine. There is a better way to do this, and I have seen it kind of take this shortcut before, and it's using this function called take drop, which you take 70% of the data and into one symbol and then 30% into another. So I'm actually going to regenerate the response to see if it kind of improves upon itself. Okay. So it's I think it's getting closer. It's using take and drop. Um, Interestingly, it's used normal to um, take the tabular data and convert it to a list of associations. So let's copy this and paste it in. So we don't need this because we've already defined data. We'll take normal of the data set. I just want to split this up because perhaps you don't always want to evaluate everything at once. Okay, so our training data looks like this. Okay, seems all right. This is the part where we actually do our oh, predicting. So I want to evaluate that on its own. Okay, didn't take long at all. Uh, okay, so I see what it's done here. So hmm, I wanted to use something called predictor measurements. So I'm going to delete this and kind of ask ask a more in-depth question of the notebook assistant here, uh, and say, how would I make a comparison plot to evaluate the accuracy of the predictor? Very good. Okay, so this is a nice part. Once you have your testing data, you can use predictor measurements. So yes, you can just run uh, each, row in your testing data through the predictor. But what's a, a better option is to use this predictor measurements function. So I think this all looks good. So this measurements object is the predictor measurements, and we can query this with many things. One of them being a comparison plot, and this is the result. So for the uh, for the 10 states that were used as testing data, so it looks like Florida, Oklahoma, um, Montana, I think that is. This is the predicted versus actual value of this predictor. So this is nice. This is really good. I'm impressed. It's behaving well. Um, and this is usually where I just open the floor to questions. So anyone has any questions, go ahead. You think about Wolfram or data science more broadly, or how to get started with Wolfram language. I have a question on YouTube where someone is saying that they're being taught the theoretical aspects of statistics, but feel like they need more practice on the practical side. Um, well, for that, I would encourage you to look at our Wolfram data repository or just any open source data sets, okay, and just kind of get your hands on them. Um, try and see what's out there. Try and test the theoretical things that you're learning at college. But I'm sure the theoretical knowledge will come in handy because whilst this talk has a kind of uh, what would you say, emotive title that data science is more than just statistics. Statistics is still really powerful. Okay, if you understand it well, then you really set yourself apart. And an understanding of statistics is very important for all of these, machine learning algorithms that you can use with predict these methods, for example. So yeah, I'll explain what I'm talking about here. So we have predict in if we go into this is the documentation page. If we go into the details and options, we can scroll down. Oops. And scroll down to the method section. Possible settings for method include decision tree, gradient boosted trees, linear regression, nearest neighbors, neural network, random forest, Gaussian process. So, I mean, all of these, there's so much background knowledge behind each of them that it would take you so long to learn. And I don't discourage learning all of this. It's really useful. Um, but all of this knowledge is kind of encoded in a very simple method goes to option, or don't even use the method goes to, just say classify or predict, and uh, what happens is some kind of meta machine learning which picks out the best method to use, just like we saw before with the learning curves. Okay, I think I have some questions. Is it okay to share the notebook today with friends? Yes, absolutely. Please recommend the best approach to find associations between paired values at timestamps. So I guess you mean key value pairs where the key is a timestamp, in which case, like I would say, time series is a nice option for you here. Um, so yes, I mean time series is defined as you require some T and V pairs. So let's take this example. Okay, so here's our time series. Um, you could also use something like this, where you have your T values and then you kind of thread them to the V values. So here you kind of have a list of rules. Um, and then you can, I believe this is a way you would go from a list of rules to a list of time and value pairs. So, and then you can just use like a time series on this. Okay, and then there's lots of methods of visualizing this. So here you can just use list line plot. Oops. You can also use dateless plot. So this is kind of dateless plot is set up to handle time and date values. Okay, sorry. For example, each row has a date object and two real values. Ah, okay. Yeah, so I suppose what you're asking is kind of similar to uh, the shipwrecks example, where uh, yeah, each row here has a date object, and then instead of coordinates or something, maybe we have some notion of the um, some numeric value. Yeah, it's hard to make a judgment call on what your data looks like without seeing it. But I would always try and um, start with visualizing it. Um, Perhaps you can use some kind of predictor. But sometimes our data just has no strong signals inside it, and it's down to um, it's down to people to admit that sometimes. Um, but yeah, feel free to reach out if you have any specific questions. I have got some resources at the end of the notebook here, just in case, it's where you can sign up to use the notebook assistant, um, and there's some good learning resources as well. You can also read up on the latest features of version 14, 13.1, and 14.2, where it will tell you a lot more about things like tabular and we still have some time. So I think some more questions of the notebook assistant. Um, I'm I've got time series on the mind. So let's say something like, how do I obtain the price of gold over the last 100 years? Okay, so I think it will yeah, use this built-in financial data function here. Uh, and this should return a time series, therefore dateless plot is appropriate. Oops. Uh, Great. Okay. How about price silver? Obviously, a very similar thing here. Uh, it's quite nice that I didn't have to ask the same question again. I could just say, how about the price of silver? And we're essentially just swapping them in here. Now, this does assume that data exists for that entire time period, but luckily in this case it does. Um, so what if I just say plot the ratio? I deliberately made that a bit vague because, does it mean gold to silver or silver to gold? Will it include everything on the same axes, that kind of thing? Okay. So I'm just going to copy the things that haven't been defined yet, but notice we've got something here called time series thread. So what that does, it applies a function, in this case divide, to two different time series. And in this case, it looks like has this worked? I believe the time series thread requires each time series to kind of have the same, yes, to have the same kind of sampling. So there must be some either missing data or a different kind of granularity of time used. So instead, I'm going to ask, how do I resample a time series such that um, granularity is every week, let's say? Let's say every year. Cool. So it's knows this function, time series resample. So perhaps I could put the gold or the silver prices into this. Hmm, okay, I don't think I need these curly brackets actually. Yes. So as you can see, it's not an exact science. Sometimes you have to kind of wrangle the large language model based assistant. Um, but so far, I've been very impressed with what it can do. It's I think it's really lowering the barriers to entry on a lot of these kind of computational topics.